So the first thing, it's been brought to my attention that next Thursday, July 2nd, is a holiday, no class. I can't remember a summer that we've ever had that holiday on a Thursday like that. I don't remember that ever happening. So when I made the schedule, I did not anticipate that holiday. And so your schedule says we have class that day. So we're actually going to lose the equivalent of 2 lectures in a traditional semester. So that's no good. But that's part of the reason why we took the test and now we're still staying here. We can't afford to just, take the rest of the day off. So now we're going to be a little behind. So I'm going to have to adjust the schedule. We'll just see how things go, okay? The test. So I went through this as you saw. I mean, like, 15 minutes maybe. So if there's a mistake in here, it's because I was trying to hurry. I was just making sure there's nothing crazy in here. So the first problem was an integration by parts. Now, maybe it could be done another way, but it was integration by parts. You let u be everything here. The derivative of it is here. You just have to make sure you square the 4x, so it becomes 16x squared. Then when you do dv, it has to be dx. When you go up to v, it becomes x. And then your new integral are these 2 multiplied. And when you do those 2 multiplied, you have a basic substitution. Yes? Yeah, I'll grade them and I'll get them back to you next week. All right, and then the rest of it worked out. Okay. Oh, so the answer should have been, what was that? Something like that. The next one, I initially was going to do a basic substitution, and I didn't see that it was going to work out clean. So I just went to trig sub. I realized that this meant the square root of all of it to the 5th power. And then here's your trig sub. X is secant theta. There's all the stuff off the cheat sheet. And then when you replace everything and do your little triangle, you get, at the end of it all, secant cubed theta over tangent to the 4th theta. And then rewriting everything in terms of sine and cosine, I believe you finally wind up with cosine theta over sine to the 4th theta d theta. Basic substitution, u is sine theta. Derivatives right up top. And use a little power rule. You can get here, this is supposed to say cosecant. And then you just go to your triangle and what's cosecant theta, and that's it. So that's that one. Next one, long division first. When you do long division, your second term, you can do this one with partial fraction decomposition because the bottom factors. The bottom factors would be x minus 3 times x plus 1. So you do your partial fractions on that, and you come up with your a1, a2. You split this into 2 integrals, and then you get natural logs on both of those. So that's that one. This one you could not do with partial fractions because you can't factor the denominator. So this is the one where you had to kind of play that game where you make the top look like the derivative of the bottom. So I have to basically add and subtract a 2 next to this. And so I add the 2, subtract the 2. When I subtract the 2, it creates a new integral. I already factored it out. And then this one is just 1 over u du. And this one you have to do completing of the square on. So you complete the square, come back in, and it becomes an arctan. So that's that one. This one, basic substitution. U is natural log x. Derivative of that is 1 over x, which is right there. And so this just becomes 1 over u cubed. Antiderivative is pretty clean. I can imagine you could have made that a nightmare, but it's a very basic sub, u sub. This one, integration by parts, because you know that derivative of x is going to get nicer, and the antiderivative of secant squared, hopefully. And then when you do your ultraviolet minus voodoo, your new integral is just antiderivative of tangent x, which you can go to your formula sheet for, and you're done. This was another trig sub. By the way, it could be done a different way, but trig sub, that's the way I decided to work it out. Just for your own kind of curiosity, another way you could have done that is to rewrite it. Rewrite it like this. What was it? X squared plus 4? What was that? X squared plus 4. You could realize that x cubed is x squared times x. And then if you make the substitution, u is x squared plus 1. Derivative of that is 2x dx. And so you can replace x squared with this solved for x squared. So you could replace that with u minus 1. You could replace this dx, right, x dx, with 1/2 du. And you can replace the entire denominator with square root of u. And it works out a lot cleaner if you do it that way. It's almost instantaneous that you get to the antiderivative. But you have to realize that x cubed was x squared times x, which isn't as natural to see. But this is the way done with trig sub. And go through the trig sub. I believe all of this here turns into tan cubed secant. And then you can peel off one tangent and create a secant tangent. And that's the derivative of secant. So you turn your tangent squared theta into a secant term. So just using the Pythagorean identity. Then make your substitution, and then the rest is pretty much, I'll let you think about that yourself. This one, this was the classic problem where the integral appears again on the other side and you have to move it over. So you do integration by parts once, nothing really happens, you do it again, and now the integral that you're trying to solve for appears again on the right-hand side. Here it is. So the integral you're trying to solve for is actually over here. So you add it to both sides, you get 2 of them, you divide by 2, or multiply by 1/2, you're done. I didn't do the bonus. Okay? So how is the bonus done, by the way? Anyone try? There's a bunch of different ways you go about this? Yeah. So integration by parts to start, or no? Integration by parts? That has to be the u. You pretty much have no choice. And the derivative of that is 1 over this times the derivative of what's in here, and then I don't know what your x comes up. And so you're going to have a quadratic over a quadratic, then you have to do long division, and then you have to do partial fractions on that. So yeah. So you can probably complete the square too. So yeah. Natural log and stuff, yeah. Okay, so I'll work it out. I didn't want to do that right now. Okay, so from going over that, I hope that you feel good. Remember, I will look at your work. I'll give you partial credit. If it's a problem that required trig sub and you're sitting there doing integration by parts, you'll get less credit than if you were doing partial fractions but not getting it. But I need to see the work. We'll see. All right, we need to pick up today where we left off. Come on. We left off with Riemann sums. So we were talking about, how we can find the area under a curve, and we came up with this idea of Riemann sums. And I showed you that to do one of these problems required a lot of arithmetic, and we also relied on these sum formulas, the common sum formulas. And I did one example, right, showing you underneath x squared how to find the area between 1 and 5. And then after that, we said we have this thing called the evaluation theorem, which comes from the fundamental theorem of calculus, that says if you want the area underneath the curve, then all you're going to need to do is be able to find the antiderivative of the function. If you can do that, you're in business. Uh-oh, this looks important. Maybe not. All right, so that's what we ended with, and did I do that example? I didn't do that example. We confirmed the area under x squared between 1 and 5. That's all. That's where we had ended. So now we have this example. Did anyone look online to see if these were up? They were there? Okay. So example 1, we want to find, this means we want to find the area underneath this function, right? The area between the x-axis and the function on the interval 1, 2. So if we were to graph this and just look between 1 and 2, it would be this blue section of curve here. And we want that area underneath. So let's go ahead and do that. So to do this, I first need to find the antiderivative of this, don't I? And that might require work that I do on the side and then bring back the answer when I'm done, but I think we can do this one just by looking, hopefully. What is the antiderivative of all of this here? So antiderivative of 4x cubed is x to the 4th. Antiderivative of negative 3x squared would be minus x cubed. And the antiderivative of 2x would be x squared. Yes? And what you do here is you put a bar next to this, and you put the 1 on the bottom and the 2 on top. Now, I thought we said that the antiderivative always had plus c in it. Didn't we say that? Well, here's the reason why it's not going to matter. Let's say we added some constant in here, and let's say it was c. The first thing we're going to do after this is we're going to plug 2 into this, right? And so let's do that. Let's plug 2 in right now. So this is equal to what we get when we plug in 2. 2 to the 4th is 16 minus 2 cubed is 8 plus 2 squared is 4. Then we would have plus c there, wouldn't we? If we kept that c in the problem. Then minus, subtract from that what we get when we plug 1 in. So plug in 1, we get 1 minus 1 plus 1, up plus c. Again. And what's going to always happen to the c's? They're going to cancel out. Which is why when we do this definite integral, when we're finding the actual area under a curve, we don't put plus c. We only put plus c when it's an indefinite integral. That means we don't have the limits of integration, and all we're trying to find is the general antiderivative. So it's not necessary to put plus c in this. Now, what's this answer? What is it, 11? So in that area, we would have to have some units in order to understand it was at 11 square feet, 11 square miles. Right now, it's a unitless measure. I mean, we don't have something, but we know that it represents an area. All right, let's look at the next problem or the next example. So I think that this came out a little better. I don't know how it came out printed on your paper, but this is 5x minus 5 raised to the x. So we're trying to find the area underneath that curve. I've had the computer graph it for us. So here's the graph. And what I want you to recognize is that this graph falls below the x-axis, right? It's below the x-axis from 0 to some number, right? And then from that number on to 1, it's going to be above the x-axis. So let's first just try and find an antiderivative, and then we'll come back and talk about what our answer represents, okay? Do we know the antiderivative of 5x? Yep, 5 halves, x squared. Now, do we know the antiderivative of 5 raised to the x? Well, we really didn't talk about that, did we? No. But we know the antiderivative of e to the x, don't we? What's the antiderivative of e to the x? E to the x. e to the x is an exponential function, where e is just the number e, right? 2.718 something. When we have 5 to the x, we have basically the same thing as e to the x, except we have a 5 down there instead of an e, yes? So there must be a more general formula for finding the antiderivative of all exponential functions, and it's on your formula sheet. What number is it? That's what we have to be careful with. If this were x to the 5th power, this were x to the 5th, right? The antiderivative of that would be what? 1/6 x to the 6th. We're adding 1 to the power and then scaling by 1 over n plus 1. That's the way we would integrate x to the 5th. But how do you integrate a to the x? It's a to the x divided by natural log of a. And that is formula, which one was it? Formula 5 on your formula sheet. Everyone needs to know that this formula exists. You might remember this from Cal 1, because in Cal 1, if you had an exponential function and you wanted to take the derivative, what you would do is you would just write out the exponential function, and you always had to multiply by natural log a. That always had to be here. And if a was e, this would be e to the x natural log e. What's natural log of e? It's 1. So it really just goes away. But if that base is something other than e, like 2 to the x, the derivative of 2 to the x was 2 to the x natural log 2. So when we're going backwards, we have to kill off the natural log a, because it's a constant. So when we go backwards in antiderivative, we're really scaling by 1 over natural log a, plus c out here. That okay? That's formula number 5. So let's finish off this antiderivative. It would be negative 5 to the x over natural log what? 5? And I'm going to evaluate that from 0 to 1. So the first thing I'll do, I always like to just write out 2 big sets of parentheses. This is what I get when I plug in what? When I plug in, what are we going to plug into this one? 1. So you get, that's the thing. You got to make sure you get the order right. The 1 goes in first, plug it in, get your answer. Then plug in 0, get that answer. Subtract the 2. Let's plug 1 in. Let's see, 5 halves times 1 squared is just 5 halves. Minus, what's 5 to the 1? Just 5 over natural log 5. And then let's plug in 0. So 0 is going to kill off our first term. What's 5 to the 0? 1 over natural log 5. So what do we have here? 5 halves minus 5 natural log over natural log 5, and then plus 1 over natural log 5, combining, distributing the negative, and then these both have the same denominators, don't they? So I can put these 2 together. So 5 halves minus 4 natural log over natural log 5. This would be our exact answer, meaning there's no rounding, no decimals. That's the exact value. Now, if you have a calculator, I'd like for you to figure out what that is. Where's my calculator? Of course, this will be an approximation, right, of the area. .01466, yes? So this is approximately 0.01466. All right, so let me see if this makes any sense. This is a pretty small number, right? It's a positive number, but it's kind of small. Look at the area, let's say, just this area right in here. Oh no, right in there. How many tenths are right here? 2? So that's 0.2 wide, isn't it? How tall is this? My little estimate here. 0.1, 0.2, 0.3, about 0.3 tall. What's 0.2 times 0.3? 0.6, right? The area of just this little thing right here is 0.6. And our answer is 0.01466. What's going on? Yeah, this down here is somehow being counted as negative. And that's an important thing about integrals and about definite integrals. When your function drops below the x-axis, this formula counts that area on the bottom as negative. And that doesn't make a whole lot of sense because usually when we talk about area, we don't talk about negative area, right? But this doesn't know that. And think about the reason why it's doing that. When we did our little rectangle, right, for our Riemann sums, right, we took that little rectangle. Here's that rectangle. Our x-axis was up here. The width of this thing, how wide it was, we called that delta x. And didn't we call the height the function's value? The height was this distance. But we were saying that's f of x. Well, in this case, if the point on the curve right here, that right corner of the box, is below the x-axis, then f of x is negative, isn't it? So you're taking a negative number, multiplying it times a positive, dx, that's going to be a negative number. So it's counting that as negative, and it's adding them up until it gets to here, and then it starts adding positives. So they're offsetting each other. So that's a critical thing to realize when you're doing areas. So it's not really the total area. The integral is not giving you the total area of everything. What is it really giving you? What do we call that? Like if I made $100 this week, but I owed someone 50, I netted, right? I netted what? 50. It's giving you like a net area. It's giving you the positive and the negative together and giving you that number, okay? So just keep that in mind. Here's a classic example of that. Integral from 0 to 2 pi of cosine x. I think it's obvious from the picture we have some positive area and we have some negative area. So the bottom area here is going to offset this top area. Now, what should the answer be then? It looks like it's going to be 0 because look, we split this down the middle, right? This is all symmetric, isn't it? So I know that this area down here should cancel out this area up here. And then same thing, this area over here should cancel out this area over here. So it should be 0. Let's see what the result is here. What's the antiderivative cosine? Sine, I'm going to go 0, 2 pi. And now my two sets of parentheses. You plug in 2 pi. Sine of 2 pi, 0. Then you plug in 0. Sine of 0, 0. So the answer is 0. Well, that's not very useful, right? I mean, if I really wanted to know this area, right, the area of this, the total area, not the net area, then I actually need to not go the entire distance, right? I need to stop it from offsetting itself. So how could I get this total area? Go 0 to the first x-intercept, right? And that would give me this area. And since they're all symmetric, I could just take that area and do what with it? Multiply by 4, right? So this right here is the net area. If I wanted to get the total area, I could go integral 0 to, where does it cross the x-axis? Pi over 2. Everyone agree? That's where the cosine function hits the x-axis at pi over 2, and of cosine x dx. The antiderivative is the same. Oh, I forgot the 4 out front. Sorry, 4 of them. This is equal to 4 sine x evaluated 0 to pi over 2. And now my 2 sets of parentheses. Are there any questions? What is sine of pi over 2? 1 times 4 is 4, and then what is sine of 0? 0 times 4 is 0. So the area would be what? 4. I've always thought this was kind of interesting. I don't know why, but if the total area of this is 4, then that means the area of one of these is what? 1. Or you could say like this, if you take the sine curve, right, like this, and you look at this one arc right there of the sine, the area of that should be what? 2. I've just always thought that's weird that it turns out to be such a nice number. That the area right there is 2. And then the area down here would be -2. They'd offset and become 0. Net, it would net 0 for the sine curve, but if you look at just that first little arc of it, it's going to be 2. Okay, so if we ever need to get total area, we will have to be able to find x-intercepts of the function, won't we? In this case, we also use the symmetry of the problem to be able to do 4. But if it wasn't symmetric, we would have to break the integral up into different pieces. Let's see what our next example looks like. Like this one. All right, so there's the graph just to help us see what's going on. I know that my net area is going to have, some positive and some negative, right? Together, it's going to offset. Let's find the net area, all right? Not the total. Let's just do the straight up integral here. All right, so first thing we need is to be able to figure out the antiderivative of x cosine x, which isn't as obvious as everything we've done up to this point. So how would you find the antiderivative of that? You do integration by parts. So down here, this is going to be my scratch work. I'm just going to work on this antiderivative. And you do ultraviolet minus voodoo thing, right? So let me see. X sine x minus integral voodoo should be this. I'll write it out. That's just so you see what I did here. And so we should get x sine x plus cosine x plus a constant. So this is our antiderivative. We would have to figure that out. And then we come back and we plug it in, but we don't need the c. So it's x sine x plus cosine x evaluated 0 to 2 pi, which is, so let's plug 2 pi in. What is sine of 2 pi? 0, so it doesn't matter what's in front of it, right? 2 pi times sine of 2 pi, that's all 0. What's cosine of 2 pi? 1. Then you plug in 0. That kills this first one off, right? And what's cosine of 0? 1. Which is 0. But these are not symmetric, right? You can't say like, oh, okay, we just need to find the area of this and multiply by 4 or something, right? You can't say that. You need to know what this area is, what this area is, and what this area is. individually. So before we try and address that, I mean, our answer is 0, right? For this, it's 0 because I didn't say find the total area. Let me get to a couple of properties, and maybe we'll revisit that. First property, if you integrate a function from A to A, the answer is 0. Make sense? How wide's your interval? 0. I mean, you're not going anywhere. So you're saying trying to find the area under the curve between one point. It's not happening. You have to have some width in order to find area. All right, this is an important one. The integral from A to B, okay, so from left to right, A to B, is equivalent to the integral from B to A if you change the sign. So getting our areas from left to right, adding up those rectangles, is the same as going from right to left, but you have changed the sign. The reason is because when you go from right to left, your dx becomes negative. So that changes. So you have to offset that by putting a negative in front of the integral. The integral of a constant. So if you just have a constant function and you're trying to find the area between A and B, it's just this rectangle, isn't it? The area of a rectangle is very easy. It's just length times height or something like that. The width of this rectangle is B minus A. The height of it is K. So it's just K times B minus A. The integral of a constant. So I'm using K here. I'm not using C because C is usually reserved for the constant of integration. So if I have a constant in front of a function, I want to find the area under that, I can pull the constant out. So that's just like with the indefinite integrals, we could pull constants out. It still works with the definite integrals. If the function is greater than 0 or equal to 0, that means if it's above the x-axis or only touches the x-axis, then the area under it must be positive also, or possibly 0. So we're saying as long as the function doesn't go below the x-axis, then the integral's got to either be 0 or positive. And of course, if it was negative, below the x-axis, then our integral is going to be negative. It's going to count that area as a negative. So here was the one that we kind of needed before I could approach that problem up there. If you take your interval from A to B, that means the left endpoint, let's say, is A, the right endpoint is B, and you pick some number between them, C, then the integral, the total area under the whole thing should be, and it makes sense that it would be, the integral from A to C, that's this area, A to C, plus the integral from B to C to B, which would be the yellow area. So this just says that if you have a big area, you can always split it into smaller sections and do each integral and add up those answers. Now this one's a little more interesting. If f is an even function. So you first have to remember what it means for f to be an even function. What does it mean for a function to be even? It's been a while, huh? I'm going to put these up here. I'm also going to write them down, but I just want to have a place you can reference it. All right, so to be an even function means that when you plug a negative number into the function, it's the same as when you plug that number in but positive. An example of an even function, most basic one you can think of, is x squared. What happens when you plug in 2? You get 4. What happens when you plug in negative 2? You get 4. So it doesn't matter if you plug in negative or positive, it comes out with the same thing. An example of an odd function is that when you plug in negative, it doesn't spit out the function, doesn't spit out the exact same thing, it spits out the opposite. So an example of an odd function would be x cubed. So let's plug in a value in. Let's plug a value into this. How about 2? What's 2 cubed? 8. Is that the same as plugging in negative 2? No, because if I plug in negative 2, I get negative 8. So these two are not the same. They are off by a sign. So I have to account for that, so I put a negative in front. So that's what it means to be even and odd. That's what, college algebra? So this is a property of even functions. If f is even, if your function is even, then it's symmetric. What's happening on the right side is exactly what's happening on the left side. So it's symmetric to the y-axis, which means that if you integrate from negative a to a, what's going to happen is that every area over here is going to cancel out every area over here, right? Or, sorry, it's going to double. I shouldn't say cancel. It's going to double. So whatever area is here is the same as this. Whatever area is here is the same as this. So notice that if your function's even, if you ever have to integrate from negative a to a, you can instead go from 0 to a. So just go out the right side from here to here and double that answer. If you do that, you're in business. This one says that if the function is odd, then the integral from negative a to a is always 0. Notice I'm using a and a, not a and b, right? So these offset each other. This positive one gets killed off by that negative one. That actually becomes useful later. We say, oh, wait, but it's an odd function. I know that this is going to be 0. All right, so those are some properties. Let me revisit this problem now. Is there a way we could find the net area of this one? Well, I could split it into, what, 1, 2, 3 areas, right? But I would need to know where these x-intercepts are occurring. So to do that, set the function equal to 0, right? Set the function equal to 0. I also need to know that first endpoint. So let's set the function equal to 0. Find x-intercepts. I set the function equal to 0. How do you solve this? It's multiplication right there, isn't it? The only way two things can multiply to be equal to 0 is if either one of them is 0. So I set both of them equal to 0. Both factors equal to 0. The first answer, the first one is the answer, right? X is 0, we've got that. Cosine x equals 0, that's a pre-cal problem. Remember, we are looking in the interval 0, 2 pi, aren't we? That's the only place we're interested. Where is cosine 0 between 0 and 2 pi? X is pi over 2 and 3 pi over 2. So within this interval 0 to 2 pi, I know that this equation has 3 solutions. So that's what these 3 are. 0, pi over 2, 3 pi over 2. So if I want the net area, right? The net area, here's what I'd have to do. For the net area, I'm first going to do the integral from 0 to my first x-intercept, which was pi over 2, of the function x cosine x dx. Now, I'm going to just underline this with blue. I'm not trying to match it up here. What I'm trying to get you to see is, do we all agree that this is a positive area? Because the graph was above the x-axis there? Now, the next one, if I just put here plus, then this next integral is going to come in, it's going to actually be negative, isn't it? It's going to take away. I don't want it to do that, so what should I do? I could do absolute value, or I could just change it to minus, because I know it's going to be negative already, don't I? Because it's an area below the x-axis. If we do absolute value, the only issue you run into is that now you have to do the absolute value of cosine. Were you saying absolute value of the whole answer? You could do that, yes. What was it? X cosine x dx. But where am I going from? Pi over 2 to 3 pi over 2. And then how about the next one? Am I going to want to add it or subtract it? Add it, right? Okay. And that's going to go from 3 pi over 2 to 2 pi. And it's the same function. Now, if you did not know, right, if you didn't know what this graph was, like above, below, above, then your safest bet would be to calculate each one, take the absolute value, then you would have positives for all of them, and you add them up. But because we have the graph, I wanted you to see that you could just take the opposite of this one. Now, isn't this the same? You don't have to do this, but isn't this the same as this? What did I do? Change the order of integration. I switched them, right? And switching them changes the sign. That was one of the properties that we just had. That's more of like an FYI. I'm not going to do this problem. I'm done. Okay, I just wanted to see how it's set up. All right. No questions? Where's my book? I'm going to give you a homework assignment to work on. And unfortunately, because of the July 2nd holiday, we got to keep going. Got to keep moving, all right? Where are we? All right, so for homework, page 306, 43, 45, 48. So those problems right there are out of the section on use substitution, but now they're definite integrals, so you can actually compute the answer. You can get what the area is. And then, hold on, I'm going to give you a few more. What I'm doing is I'm going back to all the sections that we already did homework for and assigning you problems where the limits of integration are there. But I'm trying to mix it up. I'm trying to give you some problems you haven't done. 18, 22, 25. I'll give you about 3 from each of these sections. Page 326, 42, 29, sorry. And I know you want to do a partial fraction one, so I'll give you a partial fraction one. Page 334, 15, 16, 28. That's you. Now, keeping in mind that you would now have gone home and practiced this and gotten very good at, plugging the numbers in and all the arithmetic, we're ready to move on to our next topic here, which is, I believe it's 6.6 in the book. Improper integrals. So in this section, we are going to address two types of integrals, both of which are called improper integrals. So there's a type 1 and there's a type 2. Today, for the next, when do we get out of here? 11:30? 12:30? For the next, 40 minutes or so, we're going to do the type 1. When we come back next time, we'll do type 2, and then we'll move on. So type 1 are what are called infinite intervals. So up to this point, right, we've only looked at areas under closed intervals. So you've always had to look, between A and B and try and find that area underneath the function. We now investigate areas on infinite intervals. In this type of integral, we will face one of the following types. We're either going to be doing an integral where we're going from A, that's an A, sorry, it's hard to see that, it looks kind of like a 0, where we're going to go from A, so we're going to have a left starting point of A, but the right endpoint isn't there. It just keeps going forever. So you're trying to find the area under a curve where your interval goes infinitely to the right and stops somewhere on the left side. Or you could do the other way, where you start at negative infinity and you come to some right endpoint of B and you stop. You're saying, what's the area under that? Or if we want to get really ambitious, we can look at the area under a function on the entire number line, from negative infinity to infinity. So notice the limits of an integration are infinite. So somewhere in these numbers, which were called the limits of integration, somewhere in there you're going to have an infinity. That's what makes this a type 1 infinite intervals type, right? So geometrically, if I have a function, let's say I start here at A, let's say the function has a value there, and the function does this, what do you think the area is on the interval A to infinity if the function goes up, down, and then it goes up forever? What do you think? It's going to be an infinite area, isn't it? I mean, you can't, there's no possible way that this area under here is a finite number if that keeps going up and to the right. So it is possible that we could get infinity as an answer, an infinite area. That's not really going to be that interesting to us, right? There are a lot of functions that do this. The question, the more profound question is, if you have a function that, let's say, has some value here, but maybe it has some sort of horizontal asymptote like this, where the graph comes in, starts here, and then starts to approach that asymptote. Then we're talking about the area under here. And so that you start thinking, well, wait a minute, it never reaches the horizontal asymptote, right? Never gets there. So as long as you go out, you're going to have more and more area, right? Yes? So would it be possible for this to not be infinity? And that's where things get kind of interesting. It turns out that some functions drop down fast enough towards these asymptotes that you actually get a finite area. But it has to go fast enough. And the only way to test it is to actually compute the antiderivative and figure out what happens. Right? So it's kind of a counterintuitive thing. You know the area continues. You have some area the rest of the way. It's just, does it actually have some sort of maximum number that it never gets past? No, it never does. And that's why it's so counterintuitive. I mean, if you go out to a billion, doesn't matter, it's above that asymptote. So is it possible to still say it's not in infinite area? Let me give you another problem that this will lead us in Chapter 8, Sequences and Series, but it'll tie into this idea, I think, well. If I take positive numbers and add them up, let's just do 1/10, it's easier. If I do that, and I continue to do that forever, is that going to be infinite, or is it going to be finite? The analogy I always like to use here is, let's say we have some theoretical measuring cup that holds exactly 1 cup, whatever that is. If I take 1/10 of a cup, let's do beer, it's summer. We pour in 1/10 of a cup of beer, red beer, all right? Then that's how much is in there, right? And then we come in after that and we pour 1/100th of a cup into there of beer. And now that stacks a little bit more on, right? We got another little layer of beer that's been tacked on. And then we do 1/1000th of a cup. This is all theoretical, like we actually have a way of measuring out 1/1000th and doing it, and we're not taking evaporation and all that into account. Theoretically, will the cup overfill? So we've got some no's, any yeses? I know there are some yeses in your minds at least. All right? This would be a good time for the clickers. So instead of arguing about whether or not it overfills or not, because I think both sides could come up with good arguments, right? One side that says it's not going to overfill is going to say, those are getting too small. And the side that says it does overfill says, but they're all positive numbers. If you keep on adding positive numbers forever, how can it not eventually overfill, right? The very simple answer to this problem is to just rewrite these as decimals. 1/10 is 0.1. 1/100th is 0.01. 1/1000th is 0.001, right? 0.0001. And so what's happening is that you keep on adding a 0 each time, right? And so when you add the first two together, what do you get? 0.11. And when you add this one to that, you get 0.111. And the next one, 0.1111. And you do that forever, and isn't that just 0.111 forever? Which is exactly 1/9. If you take 1 and divide it by 9, it's 0.11111 forever. So not only is this not going to overfill the cup, you're not even going to get halfway there. If you could do it infinitely, if you could, it would be 1/9 of a cup full. It will never exceed that, though. So this is one of those first times, I think, in math that you actually get something that physically doesn't make sense, but the mathematics shows that it's got to be what you didn't think it was. Or maybe you did think, you know. Okay, so I think that hopefully that ties to this area. What we're saying is that we're trying to find the area. We know that all of this here is above that asymptote. So we know that as we go out, we still have positive area. But is it possible to still keep tacking on positive, positive on top of positive and never get past something? And the answer is yes. This, no way. The reason why this won't, well, you can just say, no way this is happening. Would you agree that, let's say that this number up here was 2. Then I could say this, if this is 1, that the area here, right, that the area we're trying to find in blue is bigger than the area in black. And the area in black is what? 1 times, how long is it? Infinity. That's infinite. So what we can show is that our area has to be greater than infinity, and the only way to be greater than infinity is if you're infinity. Right? Why are you all reacting like that? Infinity is not a number, right? Infinity is not a number. Infinity is an idea of getting larger, growing without bound. So if this one's growing without bound and this one's got to be bigger than it, then they're both growing without bound. They're both infinite. Is that true? It doesn't make any sense, okay? Because these aren't numbers. You can't set up relationships like that. Basically, 2 times infinity is the same as infinity. Infinity squared is basically the same as infinity. Does not matter. Square root of infinity is still infinite. All right, we're getting way off here. Okay, so how are we going to do these? The way we're going to approach these is as follows. If we're trying to find the integral from a to infinity, that means we have a left endpoint and our right endpoint goes out forever. Then all we do is we do the integral from a to t. So t would actually stop it, wouldn't it? We stop it somewhere, but we let the t go to infinity after we do the actual computation here. If we do that, we'll have the answer. All right, that's the way it's done. Now, I'm not here to prove why that'll work or anything like that. That's a different class. All right, we just have to trust that that's the approach. That's our definition. So let's do, oh, and then if you want to do it the other way, sorry, if you want to go from left side never ends and the right side ends at b, then what you do is you go from t to b, and at the end of all of this computation, you let t go to negative infinity, because it's going out to the left forever. If these limits exist, okay, if you actually take these integrals and then you take the limit and you get an answer, a numerical answer, then we say that the integral is convergent. Converges to something, goes to something. If these limits do not exist, remember with limits you could have a couple of things. You could have the limit exist or not exist. If the limit does not exist, then we say the integral is divergent. All right? And finally, we have this. If you want to go from negative infinity to infinity, so you want to go both directions forever, what you do is you split it up into 2 integrals. You take the integral from negative infinity to a, where a is any number here. Any number. A good number would be 0, wouldn't it? But you could pick any number. And you do that integral, and then you add to that the integral from a on to the right. If the 2 of these converge, if both of these converge, then that converges. If either one of these diverge, the whole thing diverges. It's over. Here's an example. Converge. Okay, converge is when we do this computation and we get a finite number. Divergent is when we try and take the limit and we can't. The limit doesn't exist. The reason why I can't say infinity is because if our answer is infinity, it is divergent. But that's not the only time we get divergent. Something else can happen and we can still get divergent. So just think of it this way. Convergent means you get a number, finite number. Everything else is divergent. All right? All right, so here we go. A graph of this, 1 over x squared, looks like this. Sorry, no, it does not. I was doing 1 over 1 plus x squared. Sometimes we call this like the volcano function. It looks like a volcano, except that it's an infinite peak to the volcano. It goes up forever, but the function is undefined at 0. Do you all agree? All right, so I'm going to go from 1, which, of course, the value of the function at 1 is 1, to infinity, which is out this right side. I want to know the area below that curve. Forever to the right. So since I'm going to go to the right forever, and the right side is my right endpoint, right? I'm going to compute this. This right here is equal to the limit as t goes to infinity, integral where to where? 1 to t. See, all I'm doing is replacing my right endpoint with t, and then at the end of that, I'm going to let t go to infinity. And then 1 over x squared dx. Do we know the antiderivative of 1 over x squared? So this is equal to limit, rewrite everything, right? The limit has not gone away yet. The antiderivative, I'm going to put this in brackets so you realize we're not doing anything with the limit yet. The antiderivative of 1 over x squared, you said, was negative 1 over x. Right, that's the antiderivative. But you have to evaluate it at where? 1 to t, right? So I'm going to do that. This means I have a limit as t goes to positive infinity of, and this is where I did those 2 sets of parentheses that I said I like to do when I'm doing antiderivatives. We first plug in what? T. So what happens when I replace x with t? I just get negative 1 over t. Then I plug in 1. When I plug in 1, I get negative 1 over 1. I'll clean this up. Questions? Let t go to infinity. Now you let t go to infinity. So what do you get? 1. Right? Any fixed number divided by a number that's getting huge becomes infinitely small, right? So this right here is headed towards 0, right? In the limit, when you let t become large, that thing heads to 0. And then plus 1, that means the whole thing's heading towards 1. That means this is a convergent integral, and it converges to 1. So the further you go out, the closer and closer and closer that area gets to 1. You will never exceed 1, though, no matter how far you go. I'll show you the power of the Mathematica. So what I'm going to do is I'm going to write a quick program. What I'm going to do is I'm going to have this compute the area. So it's going to integrate. It's going to integrate 1 over x squared. And it's going to integrate it from x equals 1 to t. And then I'm going to control t. And we'll go out pretty far. Sorry, one more thing. All right, there's the area. Because right now I'm integrating from 1 to 1. If I go from 1 to 1, you don't have area, do you? Right? Now if I integrate from 1 to 2, the area is 1. If I integrate from 1 to 3, oh, sorry, here's my output. What are those numbers? Let me do it this way. 1, 1, 0. Okay. It's not giving. What the hell's going on here? 1 over x squared integrating 1 to t. Has it already converged that quickly? I think it converged way too fast. Hold on. Let me just go out to 10. Okay, so there we go. That's a little better. It was going way too fast. As you can see, as I go out Do y'all understand this? I'm going out, this is my x value, 80. So I'm way out there, and this is computing the area. The area underneath it is 0.9875. The further I go out, the closer that thing is getting to what? 1. If I add one more, I'll go out to like 1,000 or something. The thing is, no matter how far I go out, though, I will never exceed 1, ever. Understand? All right. What about this one? 1 to infinity, 1 over x instead of 1 over x squared. Same exact idea, right? The only difference on this problem is that it's 1 over x instead of 1 over x squared. If you look at the graph of 1 over x, it looks like this. Looks a lot like 1 over x squared, except for like the left side is negative instead of being positive. But we know they're not exactly the same. Like 1 over x squared and 1 over x, the curves are not exactly the same. But they kind of look the same. I do have a horizontal asymptote. I'm looking between 1 and infinity. So what do you think? You think it's going to converge? The last one did. So I'm going to rewrite everything. What is the antiderivative of 1 over x? Natural log absolute value of x. I'm going to evaluate that 1 and t. Which is the limit as t goes to infinity of, now I have 2 sets of parentheses here. What happens when I plug in t? Just natural log of absolute value of t, right? What happens when I plug in 1? Natural log of 1 is 0. So what we're saying is that this integral, this infinite interval, is whatever this limit is. And what is that? Infinity. Natural log of t, let t go to infinity. All that means is look at your natural log function, which looks like this, and tell me what happens to this function as I go to the right forever. Well, the function grows, doesn't it? And it grows without bound. It takes a while. It's a little slow. It's not like an exponential function, but it does grow without bound. So I know that this becomes infinite. And therefore, what do we say about this up here? We don't say that the answer is infinity. We say that this diverges. Questions? Now, what it does mean, though, is that this area, if you go forever, is not finite. So it blows up. It gets big. 1 over x squared is finite. It actually gets small enough, fast enough that the area, as you go on, does not overfill the cup. This one just doesn't get small enough, fast enough. Which begs the question, can we tell what it would take to get small enough, fast enough? Maybe. Oh, I like this one. How about 3? About 18, 19 more minutes. Y'all hang in there. I know it's hard to come in here and take a test and then sit through more, but July 2nd holiday. It might be helpful to graph these, just, on your own, just if you have your graphing calculator, just, 1 over 1 plus x squared, graph it, have an idea of what it looks like. This was the one I was graphing earlier. It looks like this. For us, though, what we're going to do is we're first going to break this integral into two pieces. We're going to go from negative infinity to anywhere we want. And I said 0 is a good choice, isn't it? Whatever that area is, if it even exists, to this area, 0 to infinity, 1 over 1 plus x squared dx. So that's the first thing. Anytime you're going from negative infinity to infinity, you need to split it up into two. Now the first integral is a limit. But this time, I'm going to let t approach what? Negative infinity. And I'm going to be doing the integral from where to where? T to 0. If you go back in the notes, that's what I said. If you're going to go to negative infinity, then the t here gets replaced with negative infinity, and your lower limit of integration gets replaced with t. And then we're integrating 1 over 1 plus x squared dx. That is just this one. Plus, now the other integral becomes a limit. This time t is going to go where, though? To positive infinity. And the integral is going to go from where to where? Lower limit, 0. Upper limit, t. And then 1 over 1 plus x squared dx. So this one is this. Understand? Now each of those you find the antiderivative of, and then do your limit. So, but it's the same antiderivative, right? It's just that the things we're plugging in are going to be different for each one. So this first one becomes limit t goes to negative infinity. What is the antiderivative of 1 over 1 plus x squared? Careful. 1 over 1 plus x squared. Arctan. Arctan. If someone said it, I didn't hear it. Arctan x, right? That's a formula 17, with a being 1. Arctan x, we're evaluating that where to where? T to 0, right? Right? And then plus, same thing, limit, but now, whoa, t is going to go to positive infinity of arctan again of x, this time 0 to t. Doing the first one, plugging in, we get two values here. Let's see what we get. What happens when you plug 0 into arctan? Arctan of 0. What is this? What the hell does that mean? That means when you look at the tangent function, which you have to know what tangent looks like, this is tangent, isn't it? That's tangent. What you're saying here, arctangent is 0, is really saying where is the y value equal to 0 on this graph? Where does it happen? At x equals 0, right? So you get 0 here. That's the question. Where is y 0 on this graph? So we get 0 there. Now plug in t, and you just get arctan t. I'll come back to that. What's the next one? Limit t goes to infinity. I have two sets of parentheses here. I'm going to plug t in first. Arctan of t. Then I'm going to plug in 0. What's arctan of 0? We just did that, didn't we? 0. So that's going to be 0. Which leaves us with limit t goes to negative infinity of, let's see, we had in here negative tangent, arctangent of t plus limit as t goes to infinity of arctangent of t. We got to figure out what those two are. Any questions on that and what I've done? What is arctangent of negative infinity? What the hell does that mean? Arctangent of negative infinity? What does that mean? Arctangent of negative infinity? What? What does that really mean to us? Where is the tangent function? Where is the y-coordinate on this blue graph headed towards negative infinity? Where does that happen? What x value is creating that asymptote? Negative pi over 2. You have to remember that tangent goes between negative pi over 2 and pi over 2. So as you get closer to negative pi over 2, the tangent function approaches negative infinity. So backwards, the inverse tangent of negative infinity means that it comes from negative pi over 2. I hope that that makes sense. So this right here, this whole limit becomes what? Oh, and there was a negative in front of it, sorry. So this right here is negative pi over 2, right? Just this, but then negative. Negative pi over 2 is pi over 2. Plus, now this one. What is arctangent of positive infinity? What is it? Pi over 2 this time, because now you're saying positive infinity. Where is the tangent function going to positive infinity? It's happening at pi over 2. So you just replace this whole limit with pi over 2. And pi over 2 plus pi over 2 is pi. The area underneath 1 over 1 plus x squared on the entire real number line is pi. Hey, that's another definition for pi. You know, you've heard before pi is always take the circumference of a circle and divide it by its diameter, and that's pi. It's a definition for pi. Well, here's another one. It's the area underneath 1 over 1 plus x squared over the entire number line. That's not, I mean, that's what it is, but, you know, there's many ways you can represent pi. Just like there's many ways you can represent the number 1, right? You can say 1 is 4 over 4. You could say 1 is pi minus 1 plus 2. I mean, there's so many different ways you can do it. This is one representation of pi. All right. 8 minutes. Not quite sure we have enough time for the next one. What will we need to do for 4? I'm not going to do it. What will we need to do? Split it into 2. Maybe go from negative infinity to 0. Go from 0 to infinity, just like we did the previous one. And then we have to find the antiderivative of that, don't we? Integration by parts. And when you do integration by parts, and then you go back and you start to plug things in, and you plug in your t, and you let t go to negative infinity and infinity, you're going to have some issues. I like to send that home as a problem that I want you to work on. And I'd like for you to come in on Tuesday, right, with questions over that. I want you to have at least tried it. you're going to run into what are called indeterminate forms, where you have something like, I'm not telling you exactly, it's going to be exactly this, but you're going to have something like, I'm waiting for people to jot it down in case they need it. Like what happens if you did this? If I took the limit as t went to negative infinity of t e to the t. Or you know what, let's make it a little easier. How about this? So what's this? What's happening here is this is headed towards infinity, isn't it? And then times e to the negative infinity. What is that? What is e to the negative infinity like? It's the same as 1 over e to the positive infinity, isn't it? Negative exponent means drop down. 1 over a number that's getting huge goes to what? 0. So this really looks like infinity times 0. And infinity times 0 is something we don't know. We have to do something with it. So these, in Cal 1, were called indeterminate forms. We used L'Hopital's rule, but we can't use L'Hopital's rule yet because it doesn't look like L'Hopital's rule. The conditions, you have to have infinity over 0 over 0. So we have to actually mess with this a little bit. I want you to do that. Now, I still have 2 minutes. I'm going to let you go early, don't worry. But I want to show you the value of this stuff, all right, like where this stuff is used. Anybody ever heard of the standard bell curve? Something like this? It's a bell curve. Standard bell curve comes from the idea of a standard normal distribution. So you have, if you take all of the people, let's say, all the males on the planet, right? All the males on the planet. And you asked, or you saw how tall they were, right? You would have an average height. And let's say that average height is whatever it is. I don't know. I don't know what it is. 5'10"? So what, like 60, let's just say like 65 inches. Right? Let's just say. Then what's the probability if you randomly pick someone now and measure their height, what's the probability that they're 80 inches tall? Small, right? If the average is 65. And so what this little height right here in this curve would represent is the probability. The one in the middle has the highest probability because that's the average. And so as you go further away from the average, the probabilities go away. Now, do they ever go to 0, though? I mean, theoretically, do they ever go to 0? I mean, what's the probability of having a human that's 800 inches tall? Can you say 0, though? I mean, can you say 0? Maybe heights aren't a good thing, but I mean, you still can't say 0, though, right? I mean, you can't say that it's impossible for someone to be 800 inches tall. It's just the probability is so infinitesimally small, right, that we can almost throw it out. What you want, though, with all this is called a probability density function. With all probability density functions, what you want is that the total probability is 1. It's almost like if you take this will be an easier example. If you take a coin, not a coin, a 6-sided die, right? 6-sided die, and you roll it. You can get a 1, a 2, a 3, a 4, a 5, or a 6, right? Those are the only possible outcomes. What's the probability that you'll get a 1? 1/6. I could graph it. That's 1/6. What's the probability of getting a 2? 1/6. What's the probability of getting a 3? 1/6. They're all 1/6, right? If you add up all of these, 1/6 plus 1/6 plus 1/6, what does it equal? 1. The total probability has to be equal to 1. Always. The probability of all the events together must be 1. So when we're looking at probability density functions like this, we want the total area underneath it to be 1. So the problem we just did, if I wanted this to qualify as a probability density function, the function I'm talking about is this. If I wanted that to qualify as a probability density function, what I would do is I would do 1 over pi times 1 plus 1 over x squared. This, right here. If I define this as capital P of x, that would be a probability density function. Because the area under it in both directions forever is what? Well, it was pi, wasn't it? But I scaled it by pi. So that area would be 1. And now it's a probability density function. And if you've ever seen the standard normal probability density function, let's see if we can get the function. Come on. There it is. This is, for standard normal or bell curves, this is the function right here. If you look at that function and graph it, it looks like this. And the area, the area underneath it is 1. What they had to do is figure out what the antiderivative of this was, and then they had to scale it by 1 over the square root of 2 pi. That's what was required in order to make it be 1. The problem with this is that nobody in this class at this point can integrate that function. E to the negative x squared over 2, that function is impossible to integrate with every technique we have. It can only be done using power series, which we haven't studied. So I don't want you to go home and like verify that the area under that is 1, because you can't do it. All right? Very, very famous, very important density function. And it just ties to the idea of finding areas under curves in both directions forever. Okay, goodbye. Have a good day. Have a good weekend.